In this chapter, we will discuss two important reactions, substitution and elimination. If you recall, we previously mentioned four types of reactions. Two of those we will discuss in detail in this chapter. We will start with substitution. Name itself says what it is. In this reaction, one species will substitute or replace another. Specifically, nucleophile is what replaces the leaving group. As a common substrate, in this chapter we will see an alkyl halide. In a typical SN2 reaction, we have a good nucleophile reacting with the primary alkyl halide. The approach of the nucleophile on the substrate happens with the backside attack, meaning from the opposite side of this carbon-bromine bond. This reaction is one-step mechanism, which means bond is forming between azide N3 and carbon at the same time bond is breaking between carbon and bromine. This is the only step of the mechanism and therefore rate-determining step. In this rate-determining step, two species are participating and the overall rate of the reaction depends on concentration of two species, nucleophile and alkyl halide. That is why this reaction is called bimolecular nucleophilic substitution or SN2. We mentioned already that this reaction is one-step process. Bonds are breaking and forming at the same time. And during that process, the energy maximum or a transition state looks like this. There is a partial bond between a nucleophile N3 and carbon and a partial bond between carbon and bromine. Because of the partial bonds, we also have to place partial charges delta minus on N3 and Br. Carbon, methyl group, and two hydrogens are in one plane, orthogonal to the N3C-Br plane. Because of the backside attack, after the reaction is finished, the arrangement of atoms is inverted. The last thing to do is to add brackets and a double dagger, as this is the symbol we will use for a transition state. Previously mentioned inverted arrangement of atoms will have significance if we are dealing with the chiral molecules. As a consequence of the mechanism, this reaction will result in the inversion of stereochemistry. Now, your homework will be to determine the relationship between those two compounds. Are they enantiomers, diastereomers, constitutional isomers, meso, or neither? So, what favors the SN2 substitution? First, and the most important thing, is a primary alkyl halide. SN2 can happen with a secondary alkyl halide, but never with a tertiary one. Also, worth mentioning that even primary alkyl halides that are branched will not be a good candidate for SN2. Here is one example. Second, good nucleophile is important for SN2. To decrease the chances of E2 as a competing reaction, nucleophile should be a weak base. We will talk more about this later. Next would be a good leaving group. Leaving group ability increases as we go down the group of periodic table. Solvent is also important, and aprotic polar solvent favors the SN2 substitution, such as acetone, DMSO, or acetonitrile.